Okay, let's get started. You may have some questions over homework. Yes? Let me address that first. So what can I discuss? Number what? Yes, Okay. Number 37. What the heck is that blue thing? Okay. Yes. Okay, so the question here is, or what they're asking you to do is write each expression as a sum or difference of logarithms. I call that in class expanding this. Right now we have a single log. We want to write it as separate logs. So we need to recognize that we have in here the operation of multiplication, right? There's a dot there next to the 25 in the x, or between the two. So I can use a property that says I can split this into two logarithms. The first one would be log base 5 of what? Hello? 25, thank you. Plus another log base 5 of x, thank you. Okay, that's the first step. And then there's one more thing you can do, and this is going to be important as we progress through today. When you have log base 5 of 25, you have a number here and a number here, right? Over here you have a number and then a variable. So you don't know what x is, so there's nothing more you could tell me about this. This one is actually asking the question, 5 raised to what power is 25, right? That's what it's saying, 5 squared, right? So because we can look at that and figure out what it is, we replace that entire expression with 2. So it just becomes 2 plus log base 5 of x. We can't do anything with the log base 5 of x, so we box it. Right? So, I mean, think about this on the side. If I wrote log base 5 of 25 and I asked you what that was, right? Question mark over there. Then you would do almost like the little loop, and you would be saying to yourself, what, like 5 to what power is 25? And since we actually know what that is, we can write that as the answer is 2. So if you know it, yes. If you know it, you go figure it out. Yeah, like if this was 5 and this was 20, you couldn't do it. You would just leave it as log base 5, 20. Yes. You can name it whatever you want. Yeah. In this problem, I wouldn't use x only because you already have x here. That's the only thing I would say on that problem. Call it whatever you want. I used a question mark, but you could call it, M if you want. What else? Go ahead. 63? Okay. Okay. Yes. X over x minus 1 plus natural log x plus 1 over x, and then minus natural log x squared minus 1. All right, so the instructions here are to write this as a single log. We have 3 logs. So we have addition between these two. We have subtraction between these two. We're going to do the addition first because we're supposed to do it in order from left to right. So we want to put these 2 logs together using the property that says we can condense 2 logs into a single log, and you will multiply whatever was in each one. So I have the x over x minus 1, that was in the first one, right? Times whatever's in the next one, so x plus 1 over x. That's what my first log is. And I'm just going to rewrite everything. Okay. Now notice, I already heard someone say it, these x's will cancel, right? Because it's multiplication there, you can cancel them. You can't cancel these x's, right? You can leave it as x plus 1 over x minus 1. Okay, so here's where I am. I say this is equal to this, which is equal to natural log x plus 1 over x minus 1, minus, then we still have this log. And I would hope that already you're thinking this is the difference of squares, but I'm not going to deal with that until after I do the condensing of these two into one. So repeating the process, putting these two logs in together into one log, but because there's subtraction, I'm going to use division instead of multiplication. So this becomes a single log. I'm going to have division. The thing that goes on top is the thing that was in the first log. So I'm going to put x plus 1 over x minus 1. And the thing that goes on the bottom is whatever was in the second log, which is x squared minus 1. Yes?
Since you crossed out the x's, do we have to take special considerations that x is not
We're not asked for domain here. But if you were looking at the domain of this, you would know x can't be 0 here. You would know that x couldn't be 1. Right. And you would also have to figure out what makes this entire expression bigger than 0. Because remember, for a log, you would have to consider that, right? I mean, there would be a lot involved if you were asked, if you were given this and asked to look for the domain. Now, if you've simplified it to this, you're going to lose that x. So you would lose sight of the fact x couldn't be 0. So to answer your question, you would have to, if it was a domain question, you would have to say x can't be 0, even though you canceled it out. I don't plan on doing that to you, but okay, I'm going to take this to the next page. And what I'll help you recognize is that you have a complex fraction. You have a fraction over a fraction. So that becomes the same as multiplication of the reciprocal. So this becomes natural log, the top one, x plus 1 over x minus 1. Now times the bottom one flipped, 1 over x squared minus 1. Which I'm about to do the difference of squares. I'm going really slow here. Natural log, this is x plus 1 over x minus 1 times 1 over. Now factoring difference of squares, x plus 1, x minus 1, like this. Cross that out. X plus 1 will go away. And the only thing that's left is x minus 1 times x minus 1, which is x minus 1 squared. So I could write this like that. That, I would be pretty happy with that on a test. I would be even happier if I saw you do this. Raise it to the -2, because that's the same thing. And I would be elated if I saw this. What did I do? The property of logs that allows you to pull a power out front. So my guess is that's the answer in the back of the book. What is this, number 63? Yeah, that's probably, is that what they have in the back? Had they got that? Yeah. See that, though? Everyone understand? This whole thing on the bottom square is the same as this whole thing on the top to the -2. That very important property of logs that I said is used a lot. Pull that power out front, and you're done. Okay? And then last one I'll do is what? 90 what? I was going to say, page 447, number 97. Solve each equation. Okay, yep, all right. So this is off of a different homework assignment? Or no, I gave these both last class, right? Yep. Okay, number 97 is log base 3 of 243 equals 2x plus 1. Okay, now there are two ways that I think you could go about this. Like I just said, if you have a log and you have a number here and a number here, you might want to check to see if you can think of what number I raised 3 to get 243. Is it 5? Now that was something you would have to check. Now, if you didn't know that, you would have to use the loop and do this, right? If you do that, you get 3 raised to the 2x plus 1 must equal what? 243. And now you're back to the situation of trying to rewrite these with the same base. So you're back to having to determine that 243 is 3 to the 5th, which is what you could have done in the very beginning. You see what I'm saying? Like at the end of the day, you still have to understand that 243 is 3 to the 5th. Go ahead. That's what we're going to start with today. Yep. We still don't know what to do if we can't write these with the same base.
I wouldn't know. I didn't know that 3 to the 5th was 243.
Why? I'm just kidding with you. So what do we do here once we've established that? Set the exponents equal to each other. And now that's just a linear equation. So subtract 1 on both sides and divide by 2. So your solution is 2. Now, the original problem was not a log equation because this x was not inside the log, right? So I don't have to check the answer for a domain. I'm okay. All right. This is actually a really good problem to possibly start with after I show you our first note for today. Well, let me see which one. Which page? Back on the other one? 47? Wait, what page are you talking about? 457? 447. And number 47. 1 to infinity. Yes. Yes, because the natural log of x had to be bigger than 0, and that only happens when it's past 1. That's right. Yep. Yep. I do, but I don't think I'm teaching it anytime soon. $45. Find the domain. Is that what you're asking? Okay, it's the last one I'm doing. The reason why, I'm trying to get through the material. I don't want to be lecturing all Tuesday and then you coming in here and taking a test 2 days later. I'd like to have some time for review. So every minute we spend doing something that was homework is time that we're taking from the review. You know what I'm saying? Okay, so this is asking what's the domain. So when you're looking at domain, you have to first look at the argument of the function, and you got to make sure that that is always greater than 0, correct? That's how we do this? All right, so the way we solve this is a rational inequality. We multiply both sides by x here. And on the right, you still get 0. And on the left side, you should just get what? X plus 1. So x must be greater than -1, right? But that's not it. That's not done. Here's the reason why. Because with the rational inequality, you have to also take a look at when the denominator would be 0, which would be when? If x is 0. So x can't be 0 also. So x has to be greater than -1, but it can't be 0. So on a number line, it looks like this. Here's -1, here's 0. We can be greater than -1, which means to the right of it, but we can't be 0, but we can go past 0. The vertical, no, yes, exactly. This would be here to here. That would be our domain. Everything between -1 and 0, not 0 though, so jump over it, and then 0 on to infinity. Okay, now, today. What is today about? We have one more note in section 5 of this chapter, and it's the great change of base formula, the wonderful change of base formula, the almighty change of base formula, whatever you want to call it, all right? Here's what it says. It says that if you're trying to find the log base A of something, all right? And this x, you know what, let's not make it an x. Let's just, for the sake of simplicity and not confusing you, that it's not a variable. Okay, let's just say these two are numbers. They don't have to be, but let's start by thinking they're numbers. We said this means a to some power is b, right? And if we can think of it, great. If we can't, then we're stuck, right? This formula says that this is always equal to the natural log of b divided by the natural log of a. And that's the formula. Now, I am not here to prove this to you today. I'm not going to go through why this formula is correct or true or anything like that. It's kind of beyond the scope of what we're going to be doing in this class. But I just want to show you what this means in terms of what we've done. The problem that we had a little while ago said log base 3 of 253, right? Wasn't that it? And the answer was 5? Was it 240? 243. Yeah. This, if I didn't know the answer is 5, right? Then what I could do is I could get on my calculator and I could do natural log of what? 243, and divide that answer by the natural log of 3. So get your calculators out and try and see if you can do this. Everybody's calculator is going to be a little bit different, all right? So, right? Natural log. So if you don't have a calculator still, I've asked you to bring your calculator, right? If you come to the test and it's the first time you've used your cousin's calculator because you never did it before, don't come ask me how to use it. I'm not going to help you, all right? You can't use your phone on the test. So whatever calculator you want to use on your exam, you need to get acquainted with that calculator before you walk into that exam, all right? So I get 5. Anybody that have a calculator not get 5 or have trouble typing this in? No? Did you get 4.9999 or something like that? No? You just got to make sure you use parentheses correctly. So this is 5 according to my calculator. You use the natural log key. ln. Yeah. How would what? Type in, hit natural log, and it should put a parentheses, put 243, close parentheses, divided by natural log again of 3, and then close parentheses, hit enter. The important thing is that every calculator is a little different. Like yours is different than his. So you just have to make sure you understand how to use your calculator. I don't want you running into an issue with this. Okay, now this is extremely powerful, all right? And this answers the question, you know, if you bought this calculator, and it's supposed to be a scientific calculator, like mine, this one's a $150 calculator, why does mine only have a natural log key? If you could have log base 4, or log base 7, or log base anything, right? Well, positive bases, not 1. If there's infinitely many bases that I could have, why only have 1 key? Because you only need 1 key. That's what this is saying. It doesn't matter what log you ever have, you can always convert it into this. So here's another example. If we're trying to solve this problem here, 2 to the x equals 5, right now, we can't think of a number you raise 2 to in order to get 5, right? So we'd be stuck. So last class what we learned is that there is a way to get this x out of the exponent. The way to get it out is to pull it out front, but you can't just pull it out front, you have to have a log in front of it, right? So what I'll do is I will take natural log on both sides of the equation. Natural log of 2 to the x equals natural log 5, okay? So what I've done is I've taken the natural logarithm on both sides of the equation. You with me? It's kind of like when you added something to both sides or multiplied. You're not doing addition or multiplication or anything. You're taking a function on both sides. So what you do to one side, you did to the other. And now you're allowed to drop the x out. So drop the x out front, and it'll become x times natural log of 2, which equals natural log 5, right? And now divide both sides by natural log 2. And what do you get? Well, you have to do that on your calculator, right? Now, I did not use change of base formula here, okay? I did not. But you can see that this right here is going to pop up a lot. This is the way we go about solving exponential equations. We try and drop that exponent out. Approximately 2.321. And, you know, we're going to go like 3 decimal places, something like that, 3 or 4. When we get to the application problems, which I'll try and get to at the end of today, where we're doing like carbon dating, we're going to talk about like carbon dating, and we're going to talk about radioactive decay. There we want to go more decimal places to be as accurate as possible. Okay, you get the idea here? Okay. See if there's anything else I want. No, let's move on. Okay, 6.6, log and exponential equations. So we've kind of come to the pinnacle of this, of everything we've been doing. The whole idea is to be able to solve logarithmic and exponential equations. Equations that we didn't know how to solve before we started this chapter. So here's your first example. I want us to solve oh, I'm in the wrong section. I'm like, what the heck? Those don't look right. Okay, let's solve this first. 2 log base 5 of x equals log base 5 of 9. All right, so we have an equation, don't we? We have a variable. We want to get that variable by itself, say x is equal to something, right? At the end of the problem, say what the solution is. So, I'll point some stuff out on the right side. Do you remember this thing? If a to the x equals a to the y, then what could you say about x and y? They had to be the same. We also have this property. If log base a of x equals log base a of y, then what do you think has to be true? X must equal y also. So if you have the same logs on both sides, and they need to be equal to each other, then what's in them has to be the same. Do you understand? So do I just say x must be equal to 9 here? Why not? Because the 2 out front. So I can't have this 2 out front. And it would not be smart to divide both sides by 2, because then you would have a 1/2 out here, wouldn't you? You'd have the same issue. We need just logs, no numbers in front. Well, 1, I guess you could say. But I already heard it. How can we get rid of this 2, or how can we move it around? Push it up to the exponent on x. So we could say log base 5 of x squared equals log base 5 of x, or 5 of 9. And now we have same logs on both sides. We can set their insides equal to each other, right? So from that, I can say x squared must be 9, which means x must be plus or minus 3, because you take the square root, you have to do plus or minus. But we have to check our answer because it was a log equation and the x was in the log. Can I plug positive 3 in here? You can have a positive right here, right? Because the argument is x, you plug in 3, it would be an argument that's a positive number, that's okay. You just can't have a negative argument, right? So plug negative 3 in here. Does it work? No, you're not allowed to do that. So you are going to throw out the negative, but it won't always get thrown out, so we have to check it. If we plugged it in here and this argument wasn't x, it was something else, like maybe the argument was, yeah, negative x, or like, you know, something where when you plugged in the negative 3, it still was okay. So x equals 3 only, since negative 3 can't be evaluated. All right, that one's pretty straightforward because that's what's considered to be a log equation, right? Where you have logs on both sides. You just try and get them to be log and then set the insides equal to each other. Let's compare that to the next example where it won't be so easy. All right, so let's try log base 5 of x plus 6 plus log base 5 of x plus 2 equals 1. All right, so we do not have logs on both sides of the equation, do we? And we have this 1 here, and that 1 is going to be a pretty big issue because the 1 kind of prevents me from just moving one of the logs over. If that was a 0, I could just move a log over, then I'd have logs on both sides. But I can't because of the 1. But these are the same logs, right? Meaning that they have the same base. And because they have the same base, I can actually turn that into one log, can't I? I can condense those into one log. That's what we did in the previous section. Right? I'm going to put these two together, and this will become log base 5, and I'm going to multiply the insides together, right? So it'll be x plus 6 times x plus 2, and then still equals 1. Are y'all all right with that? Okay, now, the whole reason why I wanted to get it into one log wasn't to use the property we just used, because I don't have a log on this side, right? But what I can do now is the loop. See, I could not do the loop here because we had two different logs. You don't do two loops. We never did that. It's always, if you had one log, you could convert it into a different expression by using the loop. So let's see what this loop tells us we have. 5 raised to the 1 must equal that, right? 5 raised to the first power, not 5 times 1, must equal x plus 6 times x plus 2. Y'all still with me? So we have here this. All right, so now we have a very critical juncture of the problem. This side is factored, okay? The mistake that students make, and will cost you dearly on a test, is if you take each factor and set them both equal to 5. You cannot do that. When we factor things, we always had to have it set equal to what? 0. And so you cannot use the 0 factor property if this side is not 0. So what I'm going to have to do is I'm going to have to multiply this out. When I do that, it's going to be a quadratic, isn't it? And I'm going to bring the 5 over, and then I'll have 0 on that side, and then I'll solve whatever equation's there. But you have to do that step. If you don't, it's really wrong. So there. So I have 5 equals x squared plus 2x plus 6x, which is 8x, then plus 12. Now subtract 5 on both sides. right? And now this is a quadratic that I can try and factor. I actually don't like writing them that way. I like to always have the 0 on the other side, so this is the same problem, isn't it? And now see if you can factor this. 7 and 1 plus 7 plus 1. Hey, what if you couldn't factor it easily? Quadratic formula. So what are my solutions here? I have two of them. X is -7 and X is -1, right? So now you're thinking, okay, I've got two answers, but we have to check them. And then you look at them, you say they're both negative, so they throw them both out or what? No, you have to actually see what happens when you plug them into the original problem, which is way up here. Original problem. Let's try and plug in first -7. If I plug -7 in here, -7 plus 6, -1. Can't do that. Can't have a negative in there, right? So automatically, I'm going to throw out the 7. -7, sorry, I'm going to throw that out. But how about -1? And what if you try -1 in here? -1 plus 6 is 5. -1 plus 2 is 1. You can have that. That's okay to have. So this one will work. You don't have to check that it actually is true. You just need to make sure that the argument is bigger than 0 after you plug in your x. So this is answering kind of your question on, is it, when is it possible to have, this is an example where you have an answer that's negative, but it's okay. It works. Yes, you could have no solution at all. Yep. You just write no solution. If neither one of these worked, you would just put no solution. No real solution, but no solution. It's fine. Good? Okay. All right, so this idea of having to put them together, use the loop, have a quadratic, realize you've got to get it all equal to 0, then solve, then check, guaranteed that's on the test. Guaranteed. All right? Next one. This problem has a very similar format to the one we just did. Got two logs on one side added together. You've got a number on the other side. So it's not like the first example I did where you had logs on both sides and you just looked on the insides and set them equal. It's not going to work out that easy. But I can try and do the loop if I can put these two together. Can I put them together? Yes, they're both natural logs, so put them together. Turns into one log, natural log. Then it's the x plus 2 times the x minus 1, and then equals 2. Now what? Do the loop. How? It's E, right? It's E. That's the thing you have to remember here, is that if I'm going to do the loop, there's really an E down here. So it's up to you how you want to do this on the test. If you want to just write an E down here to remind yourself and then do the loop like that, that's okay, even though that's not considered to be great notation. I understand what you're doing. You understand what you're doing. We're on the same page. This is E squared equals x plus 2 times x minus 1, right? And then same story. You cannot figure this out. You can't set these both equal to E squared, so you have to expand this out. Get x squared plus x minus 2, right? And now, what do we do here? E squared, you're going to have to approximate this. 7.389. Let's just say 7.39. E squared on your calculator is approximately 7.389, something like that. How about we just go 7.39? That all right? Yeah. And so when I'm grading your tests and stuff, I look to see like how far you went out, and then I just base everything off of your work. I don't I don't say, oh, they didn't round the way I wanted to. I just look at what you did and then just, follow it through. Okay, so I'm going to write this 7.39 equals x squared plus x minus 2. I will subtract 7.39 on both sides so I can get a 0. Comes out to be negative 9.39, right? And at this point, I'll rearrange it. And there's no technique of factoring that you're going to be able to do to get me a solution here, right? So you're going to have to use a quadratic formula. So quadratic formula says that our answers will be x equals negative b plus or minus the square root of b squared minus 4ac all over 2a, all that thing, right? Yes? So what is negative b for us? What is it? Negative 1. It's this number in front of the x, right? But change the sign. So negative 1 plus or minus square root of, now that b that we have here, square it. So 1 squared is 1, so 1 minus 4 times a for us is the number in front of x squared, which is 1, times c, and c is what? Negative 9.39, good. All of this divided by 2 times a, but a is 1, so that. So we got to get our calculator out and figure out what this radicand is, what all this is. So I'm going to do negative 4 times 1 times negative 9.39. That's what I'm doing first. Whoa, what the hell? $37.56. Is it plus or minus? Plus, right? And then you have the 1 in front of it. So it's 1 plus 37.56. No? Yes? That's okay? So I added 1 because of this 1 out here. These numbers together in the blue, those numbers together came out to be 37.56. But I've got to add the 1 that's in front of it. Or I should say it came out to be plus 37.56. So add the 1 in front of it. So you get plus or minus square root of 38.56 all over just 2. And so now I'm going to actually get the square root of 38.56. So square root 38.56. I'm getting 6.2096 something. I'm going to say 6.21 is what I'm going to go with. Negative 1 plus or minus 6.21 over 2, which equals, and now I have 2 different scenarios, the plus and the minus, right? I can look at both of these scenarios. If I do negative 1 plus 6.21, that would give me 5.21. Then I divide that by 2. $2.61, approximately. And then I do the other one, which is negative 1 minus 6.21, which is negative 7.21, and divide that by 2. 3.61, negative. These are my 2 potential answers, approximately. I've rounded quite a bit in the problem, haven't I? So let's just check to see that they would work. Let's try 2.61 into the original problem. Yes, yes. Negative 3.61 is the other one. When I try that to plug that in, no, doesn't work. So it's gone. It is possible to have them both work. Okay, you're not always going to get one to cancel. It has to work for all of them. It has to work for everything in here. If it fails for one, then it fails. The whole thing fails. Okay, you get the idea here? All right, let's look at another example. Log 2x minus log x minus 3 equals 1. Again, this looks very similar to what we just did. 2 logs on one side, a number on the other side. What's the difference, though? It's base 10, right? And it's subtraction, not addition. That makes a big deal, right? That makes a big difference. Because now when I put these together, it's not going to turn into multiplication, it can turn into division. So I'm going to have a different type of equation here. But let's go ahead and do it. These two come together. Log of, here's my division. 2x goes on top, x minus 3 on the bottom, equals 1. Now what? Do the loop thing, 10 to the 1. So I'm going to actually write the 10 down here. That would actually not be improper notation because I have log out here. So when you have ln here, you're not supposed to write e. You're just supposed to write log base e. But so it doesn't really matter too much. So this is 10 to the 1, which is just 10, equals 2x over x minus 1. Right? This is 10 raised to the first power, right? Not 10 times 1. Someone always does that on the test. Like if this was 10 and this was a 2, they put 20 here, right? If this was 10 and this was 2, it would be what here? 100. 10 squared. So don't make that mistake. Okay, what type of equation do we have here? Rational equation. So what I'm going to do is I'm going to clear the fractions. I'm going to multiply both sides by x minus 3. I do that so that I get rid of the fraction on the right side. On the left side, distribute the 10 through. 10x minus 30 equals whatever's left on the right, which is just 2x. This is a linear equation, so just solve for x. So subtract 2x from both sides, move your 30 over. I think you get what, 8x is 30. And then x is 30 over 8, which is, what goes into both of those? 15 fourths. If we reduce it. Yeah. So we could figure out what that is, but I mean, I'm just going to leave it as that exact answer right there. We know that that number is a little bit bigger than, well, it's bigger than 12. I'm sorry. Bigger than 3. You know what I was doing there. It's bigger than 3, right? This is bigger than 3. Where? Which, this? Log 10, yes. Remember, because it wasn't written, it was just said log. The base wasn't written. In the original problem, the base was not written. So when the base is not written, it says log, that means base 10, always. Yes. Yes, that could have been a 2 over here. 10 squared would be 100. This side would be 100 now. Yeah. I'm not sure what you're asking. You mean like writing it down or? Oh, yeah, yeah. The reason I left e squared is because e squared wasn't something where we were like, you know, like 10 squared would be 100, it'd be done. So yeah, get that number. Do this raising. Do it, figure out what it is, put that number here. Okay, does this work? This is a little bigger than 3. 2 times something bigger than 3 is bigger than 0. A number that's a little bigger than 3 minus 3 is still bigger than 0, so that works also. So this solution is good. We all right? Not so bad? Okay, how about this last one? We're moving along pretty good here. Log base log base A, I'm not telling you what the base is, of x plus log base A of x minus 2 equals log base A of x plus 4. Now you have logs everywhere, don't you? Which our first example, we had logs on both sides, didn't we? The first example. And when we had logs on both sides, then we just looked at the insides, didn't we? But we had a single log on one side and a single log on the other side, didn't we? Here we have two logs over here. So if I'm going to try to do what I did on the first example, I need to first get those two logs together. Put these together. That's log base A of what? X times x minus 2. Good, right? That's what that is. The other side is log base A of x plus 4. Now, do you have a single log on each side? You don't have any numbers in the front that you have to worry about, right? So we should just be able to set the insides equal to each other, the arguments of each side to each other. And that's what we do. So we set x squared minus 2x equal to x plus 4. I distributed on the left side before I put them. I did that multiplication through. What type of equation is this? Quadratic, because of the squared, right? So let's get everything to one side. I will subtract x. I will subtract 4. So x squared minus 3x minus 4 equals 0. Do y'all see that the log, that the base being a, actually played no part in the problem? Didn't matter what the base was? Because once I got it to here, it didn't matter. Well, they had to be the same base, but after that, the log's gone. So you don't have to do a loop. So we never had to do like a to anything. So it just works out. This factors? X minus 4 plus 1. X plus 1. Two solutions. 4 and negative 1. Does 4 work? Let's see. 4 yes, 4 yes, 4 yes. Does negative 1 work? Nope. So the only answer we have is 4. I'm sorry? Well, if we put 4 in, it's 8. You're thinking 4 minus 4? Yes, you can't plug 0 into log, so that would have been a very big problem, yes. Could be because it's Friday, you know. You ready for the weekend? I know, I'm kidding. It feels like Friday, right? No? Feels like Monday? Yeah, it should be Friday. Everyone's ready to check out. Okay, everything we've done, this example, the previous ones here, right? These are all called log equations. They're called log equations because the variable you're trying to solve for, x, lives inside of the log. So they're called log equations. Now we're going to look at something we already investigated, and that's exponential equations. All right, so let's take a look at some exponential equations. We'll call this 6.6.2. Exponential equations. I don't know what that was. Here's our first example. Let's say I have 3e to the 2x minus 4 plus 8 equals 0. No, that's not going to work. Make it 15. All right, this is an equation, right? Is it a log equation? No, you don't see a log, do you? And even then, the x has to be in the log for it to be a log equation. I want to know what x is, which makes this equation true. So I've got to get that x out of the exponent. The only way we know how to do that is by coming in with the log in front and dropping it down, right? Yes? Pulling everything out in front. But I cannot do that until I've got this exponential expression isolated by itself. I need to get this thing without the 3. I need to get all of this alone. So can you get this alone? Subtract 8 first, right? Don't divide by 3 first. Subtract 8. What's 15 minus 8? You know what? Let's change something real quick just to make this first problem a little easier. Well, you know what? It's not going to matter. It's still going to suck. Okay. It's still going to be a decimal answer, so no matter what. I was going to change that to 14. No, 16. What was I going to do? I don't know, 14, because then the difference would be 6, and then it would divide through. But who cares? Let's just leave it. Okay, now divide by 3. Seven thirds, right? 7/3. 7 divided by 3. Okay, I'll just leave it like that. Now, get this out of here. Now you can't just pull the x. You got to pull the whole exponent. Okay, everything comes down, but you can't pull this down until you've done what? Okay, which we have. Can't pull the power down unless I have what out here? A log, right? You have to have a log. So this is where you take natural log on both sides. That's critical. You can't, if you go on your next step on a test and you write 2x minus 4, and then you just like pull it down out of nowhere, you're not allowed to do that. But if you come in with a natural log on both sides first, you have to do it to both sides. See what I've done? I've come in with natural log on both sides of the equation. Now you are free to pull this out front. The whole thing comes down. And since it's 2x minus 4, 2 terms, I should probably put it in parentheses, shouldn't I? Okay, so I'm going to have the 2x minus 4 times what? Natural log e equals natural log of 7/3. Drum roll, please. Anybody know what natural log of e is? It's 1. Thank you. Good. It's 1. It was one of our properties of logs. Go back in your notes and look. Natural log of e is 1. So this turn log base 10 of 10 would be 1. So that's 1, which gives us 2x minus 4 equals natural log of 7/3. Look, I'm trying to get x by itself, right? I'm getting pretty close. I need to just get this 4 out of here, negative 4 out of here, so add 4 to both sides. Yep, and then divide by 2. Just leave that all alone and then divide it all by 2. Now, get on your calculator. Tell me what natural log of 7/3 is. Let's figure out what that is, and then we'll plug that answer in. We'll round it a little bit. I'm getting 0.847. Approximately 0.847 plus 4 over 2. Approximately 2.4, 2.42, something like that, right? There you go. Now, should I check this answer? Was it a log equation? No, you don't have any domain restrictions. So this should be my answer. Questions? Recap. Trying to solve an exponential equation. The exponent has a variable in it. You can try and isolate this exponential term or factor, get everything else out of here, then come in with log on both sides, natural log on both sides, use the property of logs, drop it down, and then isolate your x. Let's do another one. I always like to see what people will do with this. Anybody here tempted to turn that into a 9? What does order of operations say? You have to do exponents first, right? So if I actually gave, like, let's say this up here was squared, like just a 2. This whole thing was a 2. Would you do 9 squared, or would you square 3 first, then times 3? You'd square it first, wouldn't you? Because you have to square before you do multiplication. We cannot multiply these together because I don't know what this is. So that 3 is there to trick you to try and get you to do 9 here. You can't, right? So you could add exponents, yes. You could also move this over, right? What about moving this over? When I move this over, what do I get? 13? You know what? Let's make that a 10. I do want this one to work out a little nicer. So move this over to this side. Everyone change that to a 10? Okay, move this over to this side. What do you get? 3 times 3 to the 5 minus 3x is equal to 12. Now, this 3 that's being multiplied in front, I can get rid of by dividing it through. Divide both sides by 3 here. 3 to the 5 minus 3x equals what? 4. Now, unfortunately, 3 to some power equals 4 is nothing you can think of, right? Like if this was 9 over here, you could maybe say, oh, it's 3 squared on that side, but it's not, it's 4. So we have no other choice but to try and pull that thing out. So do I just drop it out now? No, you can't do that. You have to get the log in there first. So natural log. You could do it with any log. It actually turns out you can do it with any log. The reason I use the natural log is because that's the key on the calculator, right? And you'll see on this one we'll need that key. You okay with this? Take the natural log on both sides. Now take this and now drop it down. So we'll have 5 minus 3x times natural log 3 equals natural log 4. Now in the last problem when we did this, this turned out to be natural log of e, right? And that was 1 and we were happy about that. This time natural log of 3 is not 1. So if I'm trying to get the x out of here, what I'm going to do is I'm going to get this natural log of 3 out of here by dividing it on both sides. If I divide the natural log 3 out on both sides, right, then I'm left with just the 5 minus 3x over here. And then you did the natural log of 4 divided by the natural log of 3, right? And let me just warn you here to be careful. We are doing natural log of 4 over natural log of 3. We are not doing natural log of 4 over 3. That's two different things. This is two separate logarithms that you're dividing. This is one log, and you're doing division of the numbers inside. So don't confuse those. We're doing this. Oh, someone already got it, didn't they? 1.26? Yep. So we have 5 minus 3x equals approximately 1.26. And now we are at a linear equation, aren't we? So we can just solve for x. So subtract 5 on both sides. Negative 3.74. And then divide by negative 3. 1.245 or 25 or something like that. 25. We okay with that? Questions? Question? You all right? It's almost the same thing. It's because they're so close together. Okay. We don't need to check it because it was an exponential equation. Y'all doing all right?
So exponential and logs come first before anything. Order of functions.
Parentheses, exponents, multiplication, division from left to right, addition, subtraction from left to right. If you had a set of parentheses, yes. All I was pointing out is that this exponent has to be done before you can multiply these together. So that's why I couldn't put these together as a 9.
How do you put the ln in the formula?
Right here, from here to here? Okay. Okay, let me answer that in the proper way. Look, I told you this. If log base a of x equals log base a of y, then what did we say about x and y? X had to be equal to y. So look at this the opposite way. If x is equal to y, then I can do log on either side, put logs here on both sides of this equation right here, and it would be the same. That's what I'm doing. I'm taking an equation that's equal. This is like the x, and this is like the y, and I'm saying that's the same as natural log of this, natural log of this. Okay? So it's not necessarily a multiplication. That's a real bad thing that students will think, oh, I'm multiplying both sides by natural log. No. You are taking the natural log function of both sides. And that still maintains the equality. All right. Good question. No, that's a good question. All right, next one. Oh, wow, these are interesting. 8 to the 3x equals 5 to the 2x plus 5. Okay, you mean just do the log on both sides? As long as you have something to a power on both sides so that you can drop those powers down. Y'all okay that we have that? That's right. Let's go back to this one to say what is it that we tried to do here? What we did was we tried to isolate the part that was the exponent and the power. We tried to get that by itself, right? And then once we did that, we did log on both sides. So we could pull that power down. The difference here on this problem is that we already have something to a power isolated, don't we? So we want to get that x down. We just need to come in with a log. It just so happens that the other side is also something to a power, and the x is up there also, right? So the x is in 2 exponents. But if we bring log in on both sides, we should be able to drop both exponents down, shouldn't we? And we'll get the x's out of the exponents, kind of 2 birds, 1 stone. That's right. We have to bring the log in to do it, though. So I'm going to come in here with the natural log. of 8 to the 3x equals then natural log of 5 to the 2x plus 5. I am now free to drop the powers down in front of the logs. So let's do that. 3x, I don't need parentheses around it because it's only one term. And I still have natural log of 8 here, right? Equals, on this one, do I need parentheses? Yes. 2x plus 5, and then what? Times natural log 5. What am I trying to solve for? Okay, x is here and here, which means you need to get x on one side of the equation by itself. That's going to be a little bit challenging because this side over here has a parentheses, and I can't free the x from the parentheses unless I do what? Either put this through, right? Or divide both sides. What I'm going to do is I'm going to distribute this through. So see if you can follow this. I have 3x times natural log 8 equals 2 natural log 5 times x plus 5 natural log 5. So when you multiply natural log of 5 times 2x, the 2 cannot go inside the log. Okay, the 2 just stays out in front of it. Now what you could do with this 2 is what? That's in front of a log. You could, if you wanted to, bring it up and make it 5 squared, right? You could. I'm going to leave it because I could do that here also. I could bring this up and make it 5 to the 5th. But I'm just going to leave it there because I'm trying to get my x terms by themselves. Here's an x term. Here's an x term, right? This does not have an x in it. So let's move everything with x to the left side. So take this entire term, move it to the left. What do I mean by move it? Subtract it on both sides. So I'll have 3x natural log 8 minus 2 natural log 5x equals what was still there, 5 natural log 5. Do y'all have a headache, or y'all okay? Or you're what? You're hungry?
You can't pop the 2x out in front of it.
Oh, yeah. You could have had the x out in front here. Yes. This is all hold on. Yes. Actually, I should put a dot between there. This is times right there. Okay, that 5 is in the natural log only. Okay, the x is not inside the natural log. In fact, it'd probably be better notation for you to write it that way so that you don't get confused. Does that make more sense? Sometimes I lose sight of the fact that I'm completely comfortable with this, and that those little subtle things can be confusing. So yes, that x is not in the log. You cannot force it in there. So it's going to be out here with the 2. Okay, so now at this point, this has an x in it, this has an x in it. So if these both have x in it, how about we factor an x out? Like pull an x out. That's just mean, man. She's all sitting here like, oh, I'm starving, and so you're like, I'm hungry too. Start eating. Have you seen what's that show, Three Amigos? Old school comedy. Martin Short and Chevy Chase. And anyway, they're like, it's like a comedy. It's not that funny, but when I was a kid, it was hilarious. And they're like going across the desert on these like horses, and they're like dying of thirst, right? There's 3 of them. They're just like barely on their horses and all parched and stuff. But one of them has like a full canteen of water, and he's sitting there like drinking, like pouring it all over himself, and the other 2 are just like looking at him like it's just, and I think he just like throws it on the ground, and it's like pouring out on the ground. Anyway, that's kind of like what I thought about there. I'm so hungry. Okay. I'm pulling an x out of this. What's left? 3 ln 8 minus 2 ln 5 equals 5 ln 5. Now, believe it or not, I mean, this is all a number, right? Natural log of 5 on your calculator is a number, times 5 is a number. This 3 natural log of 8 is a number, minus 2 natural log of 5 is a number. So if I were to just divide this whole parentheses on both sides, just divide it out, I would have x is equal to a number. And that's what I'm looking for, yeah. So x equals, I'm going to leave it like this for now, and then we'll get on the calculator and figure out what all that is. You'll need to practice a few of these in your homework, okay? Because these can be a little tricky with the algebra in here. So let me get that computed. I'll tell you what it should be, and then you can go and try and get it yourself. .66, 2.67, something like that. Oh, no, I'm not getting that. I'm getting 2.66 or 67. Ooh, okay, so you need a parentheses around starting with a 3. The whole thing. So if you're typing this in on one of those calculators, it's going to be 5 natural log 5, then your division sign, then parentheses 3 natural log 8 minus 2 natural log parentheses 5 close, and then close parentheses again. The key being these parentheses right here. That groups that whole thing together as a single denominator. Yep. I rounded up. It was 2.665 or something. Yeah. Okay. All right. We got more to do. I know. If it's excitement you wanted, I'm here to deliver. Yeah, I'm a little concerned about this series that we're headed into. Yeah. Well, we almost came back. Yeah. When we got it down to about 5 with about 4 minutes left, I thought we might do it, but yeah. All right, well, look at this. And let's contrast that with this. On this one, we had something to a power on each side. I did the log on both sides. We dropped the powers down, didn't we? The one before it, I had, well, at the end of it, I had something to a power equals a number. I did log on both sides, dropped it down, and I was good, right? This one is especially bad because it has something to a power, and a number all together. If I try and do log on both sides, just watch what would happen. Don't write this down. Let's say I try and move the 2 to the x and the 12 to the other side. Okay, so let's say I move those 2 over, and then I try and come in with natural log. On the left side, I'll be able to pop that x out, right? But on the right side, aren't I going to have 2 to the x plus 12? I'm taking the natural log of the entire right side. This cannot pop anything out because the x is only acting on the 2, not on the 12. You also cannot split that into 2 logs because the only way you can split a log into 2 is if this was multiplication inside, which it's not. So you're completely stuck here if you try and do it the way that we've done it, which is why I'm showing you this example, all right? You got to see something very special happening here. All right, so if you tell me if you agree with this. Yep. Is that the same? 4 to the x is the same as 2 squared to the x? And then if you have something to a power and then all of that to a power, what do you do to these powers? Multiply. So isn't this 2 to the 2x minus 2 to the x minus 12 equals 0? Yes? You all right with that? Yeah? No? No? 12, no. 12 is not 2 to a power. Now, just, you're supposed to, like, see this first time and then be like, okay, I see that now. Like, I'm not expecting that you would have seen that automatically. Do you agree with this? Is this the same? So I said 2 to the 2, all to the x, is equal to 2 to the 2x. But that's the same as 2 to the x squared. Because you would do the same thing, right? Multiply these two, and you would get 2x. Do you agree with this? I put this in parentheses just to get you to focus on it a little bit. Y'all with me? Okay, squint your eyes. See the yellow here? They're the same thing. I'm going to make a substitution. I'm going to let u be equal to 2 to the x. And do you see what happens? What do you get? What's this first thing? U squared minus this thing, which is u, minus 12 equals 0. This is an exponential equation that actually turns out to be a quadratic form equation. And what are the things that tip you off to that? Well, there were 3 terms, right? I could see that 4 to the x is somehow going to become 2 to something squared. So I was starting to see that after all the experience of being exposed to this, right? I'm looking for that now. This is just a simple quadratic that factors u minus 4, u minus, or u plus 3, right? So what are your solutions? That's not a u, that's an x. U minus 4, u plus 3, do you all agree? Now, what are the solutions? U is 4 and u is negative 3. Are we done? No. That's what u is, right? But I was the one who came in here and switched the problem to u. So I've got to switch back now. So in this equation, I'm going to replace the u with what? 2 to the x. So I'm saying 2 to the x is 4. And over here, 2 to the x is what? Negative 3. You could now solve each of these using the log on both sides. But this one you don't need to, because you can just look and see. 2 to what power is 4? 2. So x equals 2 is a solution. This one, is it possible to ever raise something to a power and get a negative number? No. There's no solution here. The only solution is 2. You're guaranteed to have one of those. That's a classic college algebra exponential equation problem. I mean, it's just. So let me tell you what homework you should do. This is probably the most important homework assignment out of everything out of this chapter so far. You should look at page 463, and you should try. I'm going to load you up here, okay? Because practice in this section is a good thing. And what else are you going to do this weekend? Nothing. Nothing. I'm kidding. So what I recommend you do is 5 through page 463, 5 through 55 odds. That's a lot. I understand that's a lot. It's 25 or so problems. About half of those are log equations. About half of them are exponential equations. I think if you can get through that assignment, you'll be prepared for those on the test. I would say the test is going to be, 30% to 40% will be this. You got to be able to solve these types of equations. I've tried to give you a variety of things to look at with the solving. You'll have to just go home and see how it goes. Now, I do want to talk one more thing, just so, again, we can have some time on Tuesday to talk about review. Let's just do one application of this stuff, like where we could see this in the real world. So I'm going to start 6-8. Exponential growth and decay models. These are going to be word problems, yes. Okay, let's talk about I'll give you the option. We can talk about uninhibited growth models like bacterial growth. We can do that. We can do exponential decay like radioactive decay, half-lives, or we can do Newton's law of cooling, which is like you find a dead body and then like you see what the temperature of the body is, and then you can try and figure out how long they've been dead. Okay, and then the next time we come back, we'll do one other one. So I want 2 applications on the test, one of each type. There's 3 types. There's growth, decay, Newton's law of cooling, and then there's logistic models in here. I'm not going to do logistic models, so we'll do 2 of the 4, but throw out logistics, so 2 of the 3. Growth, decay, Newton's law of cooling. Cells, cooling, radioactive decay. So you want to do cells and cooling. That's what you're saying. Oh, okay, you're voting for that. We're going to do Newton's law of cooling right now. Yes. Okay, so I'm going to write down the formula the way it appears in the book. All right, U of t equals capital T plus parentheses U naught minus T e to the kt, where k is less than 0. What's that? Oh, now you changed your mind? It looks worse than it is. All right, let me explain what everything is here, okay? The detectives and stuff use this for, like, seriously, you go to a crime scene and, they go to the body, they take the temperature of the body. No, like, oh, like bones. I don't know. I haven't seen it. But yeah, I mean, if you go and you find a body and it's still warm, of course, if it's already the temperature of the room, then it's been there too long. But if it's still warm, then you can measure the temperature of the body, and then this is what you use to determine how long it's been there. Okay? Yeah, well, theoretically, right? So let me explain what everything is here, all right? You have this U of t on the left side is the temperature of an object after t time. All right, so I have to be a little vague here because the temperature could be measured in Fahrenheit, Celsius. All right, time could be measured in minutes, hours, seconds. It just depends on what this is modeling. But the left side of this equation, tells us the temperature of that object at a particular moment in time. All right? That moment in time being T. Understand? So, now what's the T, little t, is the elapsed time. Capital T is going to be the, I don't know, do you all know what ambient temperature is? Okay, this, like the temperature of this room is the ambient temperature, is the surrounding temperature. So like, you know, you take your temperature right now, it should be around 98.6, right? But the temperature of the room is like 74. So if I die in here right now, my body is going to cool down to the temperature of the room. Capital T is the temperature of the room, which they call the surrounding medium temperature. All right. Yeah. I think that's everything. Oh, U naught. Hold on, U naught. Is the initial temperature of the object. Most people are 98.6, unless they had a real high fever. I mean, it gives you an idea of how long. I mean, it's not going to be like to the millisecond, right? But we'll know if it's been there for 12 hours versus 8 hours, you know. So the initial temperature of the object. Now, this is good for, this model works good for dead people, but it also works for anything. Like if I just take a block of metal and I heat it up to a certain temperature, 300 degrees, I set it in a room that's 74 degrees, I can predict how long it's going to take for it to cool down, or if I know it was 300 degrees and now it's 200 degrees, I can tell you how long it's been there. This isn't just for dead bodies, but it works great for dead bodies too. So that's more interesting than me talking about a block of metal being heated up, right? Everyone wants to talk about dead people. All right, so we have K. So K is going to be a constant, all right? K, and they refer to K here is just a negative constant. And that's going to be dependent upon the type of object. If it's a block of lead, the way that it loses temperature is different than the way a block of steel would lose temperature, which is different than the way a body would lose temperature. So human bodies, that constant K is going to be different for each person, but we're all going to be about the same. For steel, it's going to be about the same. You know what I'm saying or not? So that K somehow dictates this exponential function, right? And it's supposed to be negative, all right? Do you remember what happens if you put a negative up here next to this t? We are looking at an exponential function that gets flipped, exactly. It's an exponential function that looks like this. And so it has an asymptote like this. Okay? That's what happens with the negative exponent, which is kind of what's modeling your temperature drop. Okay, so now let's just kind of check this. Let's say no time has elapsed. No time's elapsed. Let's just look at this formula for a second. So I'm standing here, I'm alive, right? Taking my temperature, I'm 98.6, the room is 74 degrees, let's say. Time is 0. What should this function spit out? The temperature of the object at the time. So what should it spit out? Okay, let's just check. Plug in 0 for t. What is e to the, who cares what k is, what's e to the 0? 1. Okay, So this just becomes capital T plus U naught minus T, right? And this isn't even here. The capital T and the minus T cancel each other out, and you're left with what? U naught, which is the initial temperature of the object. So the formula works. If T is 0, it's just my temperature, right? Now, if a certain amount of time elapses, what happens is this. So let's say we plug something in here, and let's just say that it spits out. We plug in a T, and let's just say it spits out 1/2. 1/2. Then what it would be is a half gets distributed through here, right? It'll be the temperature of the room minus half the temperature of the room plus half my temperature, if that makes any sense. And that is what the temperature of the body would be at that point in time. All I'm trying to convince you of is that at the initial point in time, this formula works, and as time goes on, what's going to happen is well, what does this get closer to? Yeah, this is probably a better way of looking at it. What does this function do as t gets larger? What does it do? It goes to 0, doesn't it? So if this thing is getting closer to 0 as time goes on, then that's going to kill off everything here, right? Everything here. And the only thing left would be what? Capital T, which is the temperature of the room. So hold on. At the beginning, this function gives me the temperature of me. And at the end, as time goes on, it gives me the temperature of the room, which is what should happen. If I die right now, my body started at 98.6, but as time goes on, the temperature of me should get closer to the temperature of the room. So this is a perfect model for what's happening. Let's see if we have to know it. Let's see. So let's answer a question, okay? All right. I'm wondering if I should use theirs or actually do a body. I'll try and do my own. I'll make up my own and make it a human instead. Okay, so here's the example. A person (98.6 degrees Fahrenheit), right? Dies in a room which is it says 70. It doesn't feel like 70 in here, right? Yeah, let's go with 72 degrees Fahrenheit. All right, so first question. If temperature of body is 92 degrees when found, and let's say 89 degrees 2 hours later, then what is K? What is the constant? See, you were asking, do we need to know K, right? Here's the thing. Newton's law of cooling models all things that do this, right? So we don't need to know. We just need to walk in as the investigator and say, oh, dead body, oh, it's still warm, take the temperature. Okay, let's wait. 2 hours later, let's take the temperature again. If we do that, we will get K. Then we'll have the model, and then we can answer a bunch of questions. All right, so that's our first question. Let's address this first because I'm almost out of time. So how can we do this? Yeah, let's just write the formula down. U of t equals capital T, what, plus U naught minus T e to the k little t. All right, what do we know here? We know big T. What's big T? 72 degrees. Do we know anything else? Little u. What's little u? Or U naught, sorry. Temperature of the body at the original point in time, which would have been 98.6. So here's our function so far. 72 plus 98.6 minus 72 e to the kt. We don't know anything else, do we? Let's go ahead and clean this up. What's 98.6 minus 72? $26.6 plus 26.6 e to the kt. Look, believe it or not, we almost have an exponential function here, don't we? Almost. We have e to a power. We've got a number in front of it. We got plus 72. Remember, the plus 72 moves the function up, right? This k, though, is what we need to resolve. So let's talk about what we know. When we found the body, right? When we found the body, what, 92? And then 2 hours later, it's 89. Okay. How can we use that to find k? You have to be real careful here. Okay, so 2 hours later, t could be 2. See, this is the part we have to be careful with. What does t equals 0 mean? That's when they died, right? That's when they died? I don't know when I walked in there, do I? I don't know how many hours later I walked in. What I do know is 2 hours after that, I'm able to measure the temperature again. We're not going to have enough time to do this. I think this is a good point to just get you to say, hey, why don't you think about this? Do your homework. Think about this. We will pick this up. Because what you cannot do right here is you cannot say that this is what's happening at t equals 0 and this is what's happening at t equals 2. You can't do that because that would mean that at t equals 0 the body was 92 degrees, but at t equals 0 was 98.6, right? So. But we can, but we can't say that this is what's happening. See, look, if I say this is t equals 0, then that means when I plug 0 in here, right, I should get 92 degrees, right? But if you plug 0 in here, you can get 1. And if you put these two together, you get 98.6. It's not, so this is not the temperature at the beginning. So we can't call that t equals 0. We'll be able to do it, but I think it's going to require a little more thought. No, I'll probably give you a constant on the test, or I'll give you the temperature of something at the initial point in time. Okay, we'll work on this more later. All right, you take care.